So now I'm going to go over some homework problems related to cylindrical coordinates. So in this first problem, we're trying to do a triple integral where we're over a solid E, where this solid is inside the cylinder of radius 3, centered at the origin, and centered along the z-axis. And it's between the two planes z equals -1 and z equals 1. So in the xy plane, we have this circle of radius 3 centered at the origin, and then z is just going between -1 and 1. So we set up the r and theta for our cylindrical coordinates just like we would for polar coordinates if we had a circle of radius 3. And theta is going to go from 0 to 2 pi, and r is going to go from 0 to 3. And then we can see, since we're between these two planes, this is the bottom surface, z equals -1, and the top surface is z equals 1. So we're just going to go from z equals -1 to z equals 1. So this is the setup. I have theta going from 0 to 2 pi again, and r going from 0 to 3, and z going from -1 to 1. Now I've replaced this x squared plus y squared with r squared, and when you take the square root, that's given me one of the r's here, and dv is giving me another r. dv is r dz dr d theta. So we get one of these r's from dv, and we get the other r from just rewriting this in polar coordinates or cylindrical coordinates. So this is the triple integral we want to evaluate. First, I'm integrating with respect to z, so the r squared is a constant. And I just get r squared times z then, where z is going from -1 to 1. If I plug in 1 and then subtract the -1, I'll get 2. So now we just have 2r squared. We're integrating with respect to r. This gives me 2 times r cubed over 3 when I integrate. So that's 2/3 r cubed. I want to evaluate this from r equals 0 to 3. Of course, at 0, I have 0. But at 3, notice the 3 cubed over 3 is just 3 squared. So I just have 2 times 9, which is 18. And so I get 18 in the integrand, and I'm integrating with respect to theta. I can take the 18 out. It's a constant. I'm just going to get theta. When I integrate that, I get 18 theta. I'm evaluating that from 0 to 2 pi. And so you just end up with 36 pi. So that's the answer to this problem. Let me go to 5. Now 5 is over the exact same circle we had in the last problem. It's a circle of radius 3 centered at the origin. So that's the base of this solid. So I have that at the bottom, xy plane. So we have that circle in the xy plane for the bottom. And the top, I don't know if you recognize this, if you square both sides and rewrite this, this is the top part of an hyperboloid of 2 sheets. So that's an hyperboloid of 2 sheets, the top part where z is positive. And so we're going to integrate over this circle in the xy plane. So again, just like in the last problem, theta is going to go from 0 to 2 pi, and r is going to go from 0 to 3. Z goes from the bottom, where z equals 0, the xy plane, to the top, where z equals the square root of x squared plus y squared plus 16. Now we want to put this in cylindrical coordinates, so I need to rewrite this. This will be z equals the square root of r squared plus 16. Since x squared plus y squared is r squared. And so that gives me this triple integral down here. Again, theta was going from 0 to 2 pi, and r was going from 0 to 3. And z was going from 0 to the square root of x squared plus y squared plus 16, but we replace the x squared plus y squared with r squared. And as usual, the dv, because this is a volume question in this case, is just going to be the r dz dr d theta. So that's what we're integrating. When we integrate with respect to z, this r is a constant again, so we just get rz evaluated from z equals 0 to the square root of r squared plus 16. So that's just going to give me the square root of r squared plus 16 times that r we already had. Now I want to integrate with respect to r. We want to do a u substitution here. U equals r squared plus 16. Du is going to be 2r dr. And so we want to replace the r dr here with 1/2 du. And so the integral of r times the square root of r squared plus 16 dr is going to look like just this now. We're going to have the 1/2 we can take out, but the r dr gets replaced with du and this extra 1/2. And then this will just be u to the 1/2. So we have u to the 1/2, and then the r dr is 1/2 du. So if I integrate this, I'm going to get u to the 3/2 over 3/2, and with that 1/2 there. So I'm getting u to the 3/2 over 3/2, the 1/2's in the numerator. Notice this is just 1/3 times u to the 3/2. U was r squared plus 16. So when I integrate this on the inside here, I'm going to just get 1/3 r squared plus 16 to the 3/2. So that's u to the 3/2 again times the 1/3 here, where r is going from 0 to 3. Let's plug in 3. I'm going to get 9 plus 16, which is 25. Take the square root first, since that's easy. It's 5 then. 5 cubed over 3 is 125 over 3. Plug in 0. I'm going to get 16 to the 3/2. Again, take the half first, since it's easy. It's just 4 then. 4 cubed, and that's going to be 64. So that's over 3 as well. We're going to have 125 over 3 minus 64 over 3. So that'll be 61 over 3. Integrate 61 over 3 d theta. I'm just going to get 61 over 3 times theta. Theta is going from 0 to 2 pi. So we're just plugging in 2 pi and 0, and we're just going to get 122 pi over 3. So that's the answer to that question. Now I gave you the arguments for 8 and 11 in a write-up, so you have those you can look at. And I'm going to do 9 and 12, and now we're going to look at 9. Here we want to calculate this triple integral by converting it into cylindrical coordinates. You can see it looks a little bit hard to integrate. This one you could integrate with respect to x if you wanted to. You could just square this out and then integrate it. But then you're going to have to integrate with respect to z, and you're going to have some extra square roots in there. You can have square roots. In fact, you have the square root in here coming. And it looks like it could get kind of messy. But cylindrical coordinates won't be too bad. Let's see what that looks like. We have y going from 0 to 2. And then z is going from the bottom of a circle of radius 2, centered at the origin in the yz plane, to the top of that circle. So in the yz plane, where you look at these two variables, you're going to have y going from 0 to 2 and z going from the bottom of the circle to the top of a circle of radius 2. So the yz plane, we have half of a circle. It's a circle of radius 2 centered at the origin, and it's the half where y is positive. Now, x is going to go from 0, so that's the zy plane that we were just talking about, to this sphere of radius 2 centered at the origin. So that's going to be then a fourth of a sphere. We're going to have the back of this fourth of a sphere is just going to be this half circle we described in the yz plane, and then we're going to the front of that sphere. So it's an eighth of a sphere in the first octant, and right below that another eighth of a sphere. So here's a picture, and here's another picture. So this is showing you the zy plane is this half, and this is on the other side here, the xz plane. So it's that quarter of a sphere. In the xy plane, we have a circle, and that circle you can see is, well, we have x equal to this, and when z equals 0, that's in the xy plane, you're going to have x as the square root of 4 minus y squared. So x squared plus y squared equals 4 is that circle. Same circle of radius 2 that we were talking about before, but now it's in the xy plane. So we have a circle of radius 2 in the xy plane. And so when we integrate in the cylindrical coordinates, we're going to have theta going from 0 to pi halves, because we're in the first quadrant here for this circle. And r is going from 0 to the radius, 0 to 2. So we have theta going from 0 to pi halves and r going from 0 to 2. What about z? Well, z has to go from the bottom of the sphere to the top of the sphere. So we got to imagine z going in the positive d direction. We're going from the bottom of the sphere to the top of the sphere. So this doesn't really come into play as much as x equal to this, because this is the sphere. When I said x equal to this, that's what gave me the sphere. Right? And if you rewrite that, it's x squared plus y squared plus z squared equals 4. So that's the sphere of radius 2 that we're looking at here. And we want to go from the bottom of that to the top. We want to solve for z. What's z on the bottom? What's z on the top? So if x squared plus y squared plus z squared is equal to 4, z squared is going to equal the square root of 4 minus x squared minus y squared. Don't forget, we have to write that in cylindrical coordinates. So the x squared plus y squared, we got to write as r squared. So z is going to equal the square root of 4 minus r squared. And since the way I'm saying that that's positive, you're going to be on top here. I want minus that for the bottom part of the sphere. So let me show you what it looks like. Get rid of this here. We have, again, theta going from 0 to pi halves for that quarter of the circle in the xy plane. R going from 0 to 2. And then we're looking at that sphere. Z on the bottom of the sphere is the square root of 4 minus r squared with a minus sign in front. And then at the top is just the square root of 4 minus r squared. So that's the setup for the triple integral in cylindrical coordinates. We want to evaluate this. So this is a constant when we integrate with respect to z again. So I just have this, and I want to plug in square root of 4 minus r squared, then plug in negative square root of 4 minus r squared, but we're subtracting. So I'm going to have a square root of 4 minus r squared minus a negative square root of 4 minus r squared. That's going to give me 2 square root of 4 minus r squared. So I'm going to get a 2. This 4 minus r squared to the 1/2. I also have a 4 minus r squared 2 here, to the second power. So we're going to have 4 minus r squared to the 2 plus 1/2 power, or 5/2 power. So again, we got a 2 when we took this minus this that's here. I have an r here. And then we got a square root of 4 minus r squared when we evaluated z as well. That's 4 minus r squared to the 1/2. 4 minus r squared to the second power here. So 2 plus 1/2 gives me 5/2 power for 4 minus r squared. Now I want to integrate this with respect to r. So what are we going to get? Well, if you do a u substitution, this would be u to the 5/2. We essentially have du here. Du would be minus 2r dr. So this is just minus u to the 5/2 du. So this would be u to the 7/2 over 7/2 with a minus sign. So we're going to end up getting a minus u to the 7/2 over 7/2. Now, if you divide by 7/2, it's the same thing as multiplying by 2/7. So it's u to the 7/2 over 7/2 with a minus sign, but again, that 7/2 in the denominator becomes a 2/7. We want to evaluate this at 2, we're just going to get 0. When I plug in 0, I'm going to have 4 to the 7/2. 4 to the 1/2 is 2. So we have 2 to the 7th, 2 to the 8th with that extra 2 there. That's going to be minus 256 over 7, but we're subtracting at 0, so it's plus 256 over 7. So I have 256 over 7. I want to integrate this now with respect to theta. I'm just going to get 256 over 7 times theta, evaluate from 0 to pi halves. That's just going to give you 256 over 7 times pi halves. And so you get 128 pi over 7. So that's the answer to that question. The last problem we want to look at is problem 12 from this homework assignment. Here, the integral looks kind of messy, but the solid that we're integrating over this g does not look too bad because z is just between -1 and 2. So this will be the bottom and this will be the top. And we just have cylinders. So this is a cylinder of radius pi halves. I divide by 4 on both sides. This will be x squared plus y squared is pi squared over 4. So that's a circle of radius pi over 2 in the xy plane. And here we have a circle of radius pi in the xy plane. But these are cylinders because we're in space. This cylinder and this cylinder are both centered around the z-axis. And the center is the z-axis, but the radius is pi halves here and pi here. So this is the inner cylinder. This is the outer cylinder. So when we set this up in the xy plane, again, we just have these two concentric circles, a smaller circle and a bigger circle around it. And we're going all the way around the origin here. So theta is going to go from 0 to 2 pi. The r, though, has to go from, you start at the origin and you work your way out in the xy plane. You're going to hit pi halves first and then pi. So you're going to hit the circle of radius pi halves and then the circle of radius pi. So r is going to go from pi halves to pi. And z again is going from -1 to 2, the bottom surface to the top surface in this picture. So theta goes from 0 to 2 pi. R goes from pi halves to pi. And z goes from -1 to 2. Now I've rewritten this in terms of polar coordinates or cylindrical coordinates, again replacing this with r squared, and square root of that will be r. And here we have an r also. But remember, dv is r dz dr d theta, so that extra r is nice here. It's going to cancel. So all we're integrating is cosine of r here. So I have the cosine of r dz. Cosine of r is a constant. I'm just going to get cosine of r times z, where z is evaluated from -1 to 2. That gives me 2 minus a -1 or 3. I took the 3 outside here. Cosine of r, when we integrate, we get sine of r. We want to evaluate that from pi halves to pi. I plug in pi, I'm going to get 0. I plug in pi halves, I get 1. I'm subtracting that, so I get -3. And then when you evaluate this, you're just getting theta evaluated from 0 to 2 pi. So you're just getting 2 pi from here times this -3, which gives me the -6 pi. So we're getting a -6 pi. It is negative. You can see that it's negative by looking at what we have here. This r is between pi halves and pi, and this is going to be positive. But this part we're integrating, the cosine is going to be negative between pi halves and pi. So you really just have something negative here all the time. And when you integrate them, you're going to get a negative number, the -6 pi. So this is the value of the triple integral we started with, -6 pi. And that finishes this problem, and that finishes this lecture.